we're going to just try and do organic chemistry past paper questions. And so starting with where's our organic chemistry? So starting with this one. That's about transition metals. So this one, he's saying when a benzene undergoes nitration, a nitro group substitutes a carbon atom. State the shape geometry around the substituted carbon atom in the benzene molecule, in the intermediate complex, in the nitrobenzene product. So first thing, let's quickly go through what happens when there is nitration. So here's your benzene molecule, right? Remember the structure of benzene when it's bonded to, or when it's forming benzene, that's sp2 hybridized, which means that benzene has 4 electrons. 3 of them, they get bonded with 3 different atoms. While what happens to the fourth one is involved in pi bonding. The 4th electron initially remains unchanged and it's not doing anything. So this is what happens to carbon. Carbon is only bonded to 3 atoms. So 1 electron gets pulled over here, 1 electron gets pulled over here, 1 electron gets pulled by another atom, while the 4th electron is not initially doing anything. So you can look at the benzene structure that the carbon atom is sp2 hybridized. It's making 3 bonds, while the 4th electron isn't doing anything. And all the carbon atoms are exactly identical, which is why the unused p orbital, they all start overlapping and they form a ring of delocalized electron cloud. Is that clear?
Yes, sir.
So he's talking about nitration. Bromination and nitration are both examples of electrophilic substitution. What happens is that the electrophile, the positive electrophile, pulls one of the p orbital, and bonds with it. So this is what happens to carbon, that the bromine comes in, one of the p orbital, so the carbon in the middle, in the intermediate, ends up making 4 bonds. So previously it was 3 bonds where the 4th electron wasn't doing anything, but now it's making 4 bonds because bromine came in. Is that clear?
Yes.
So the same kind of happens in nitration as well. Nitration is exactly the same. So he's talking about the geometry of the carbon atom in the question before and after in the benzene molecule. So state the shape geometry. So that one is trigonal planar initially. Sorry. So the first one is that it is trigonal planar. Right? Is this part clear?
Yes.
Like before it was fan shaped and the 4th electron not doing anything. When in the intermediate, when the NO2 comes in, the NO2 plus 1 electrophile comes in, it pulls the electron from carbon and bonds with it. Then it becomes, when it makes 4 bonds, what shape does it have? And what type of hybridization is that?
sp3 hybridized.
And sp3 hybridized, he's talking about the shape geometry. So what shape in sp3 hybridized when it makes 4 bonds?
Tetrahedral? No, yeah, tetrahedral.
So it's going to be tetrahedral. And so previously it was sp2 hybridized, but now it's going to be, it's making bonds with 4 atoms. So all 4 will be pulling all 4 electrons in 4 different directions. And in the nitrobenzene product, it's again sp2 hybridized. Like at the end, what happens is that carbon, the benzene electron cloud is electron deficient now because NO2 took its electron. So the electron cloud wants to be complete again, wants to be stable again. So what it does is it pulls the electron from hydrogen, and the p orbital over here reforms, and the H leaves. So that kind of means that it's going to go back to sp2 hybridized. It's going to become trigonal planar again, And it's going to be sp2 hybridized back again. Is that clear?
Sir.
So the next one is when naphthalene undergoes nitration, a mixture of two organic compounds is formed. Each compound contains one nitro group. Suggest the structures of these compounds. So two compounds are formed, right? Two organic compounds. And each compound has one NO2 group. So it's either going to be NO2 attached on this carbon atom, right? Because if you attach NO2 over here, it's going to be the same thing. If you attach NO2 over here or over here, it's going to look exactly the same. It's just going to be a rotated version of the same thing. Is the idea clear? Like if you flip this molecule left to right, this NO2 will come over here. If you flip it upwards, the NO2 will be on top, right? If you flip it sideways, the NO2 would be over here. So the thing is, all of these, like any of these positions, they're basically exactly the same position, right? And what is the other position? The other position is that
position?
Yes. So it's either going to be two. They don't usually use ortho and para. In CAE they use 246. Or in this case, it's actually not going to be this because there's no specific group attached. So you don't exactly know which one is ortho and which one is para. I mean, is the idea clear that in this case, I mean, 246 or 35 directing positions. I mean, if you have this molecule, then that position would make sense, but not in this molecule. Is that clear?
Yes.
But anyways, these ones, they're all exactly the same. You attach NO2 over here, that's exactly the same. You attach NO2 over here. So they're all flipped versions. So one of them would be NO2 attached over here. The other one would be NO2 attached over here. Is this clear?
Yes.
Now the next one is naphthalene can be oxidized under certain conditions to I don't know, anhydride C8H4O3 carbon dioxide. Construct an equation for the reaction. So you can construct that using O. So you have the trick in this is they're basically asking you to figure out how many hydrogens and carbons does this have. Because they actually told that as well. So it's C10H8. So everything is there. You just have to balance the thing out. That's it. This one. Reduce the type of reaction shown by this equation. So what type of reaction is happening here? Any guesses? Like what happens when water is produced? What type of reaction is that?
Hydrolysis.
So that is, hydrolysis is water getting added. So, I mean, hydrolysis is like an ester gets hydrolyzed, right? Which basically means that it breaks down and ends up forming. Now, if you look at this molecule, what is happening? What's going on? This group remains, right? I mean, it's when water is produced, that's known as dehydration, by the way. But I'm more interested in the fact, where did the third benzene come from? Right? That's a question mark. So there's actually two OH groups. So that means, if you look carefully, this thing over here is kind of connecting with the carbon over here, right? My guess is it's connecting to this carbon atom. And there's another one of this that's connecting to the same carbon atom as well. So I guess it's dehydration, but I would have to check. I can't say that you can't say it's reduction or oxidation because this is an ester group. So it's kind of the benzene getting attached to this carbon atom. Why will the benzene get attached to this carbon atom? Because this carbon atom is positively charged.
Yes.
I said, oh, sorry, there's dehydration and there's the other one, which is, this is probably a condensation reaction. Dehydration is when you have water being removed from the same molecule. Like alcohols get dehydrated, right? Is that clear? Like you have an alcohol and it gets dehydrated. You've got H, and the OH is lost and the H is lost and you've got an alkene, so water is produced, right? So that is dehydration, that you remove water from a molecule. Condensation is when two molecules join up, and when they join up, they end up producing water molecules. That's condensation. Like esters are produced using a condensation reaction. When you have an ester, two molecules are going to join up, and when they join up, they produce a water molecule. Is this clear? So it's probably going to be condensation.
Yes.
I said, then name the functional groups in addition to the benzene present in the phenolphthalein molecule. So I didn't know it's a phenolphthalein molecule. Other than benzene, what is this group?
Carboxyl.
What happens when you have a serial bond O and O somewhere? What happens when you have serial ester? That's an ester, right? So this one is an ester. What do you call this one?
Phenol.
That's a phenol. So we answered that apart from benzene. So we did that. Phenolphthalein reacts separately with two reagents shown in the table. Complete the table by drawing the structure of the organic products formed. So he's saying that phenolphthalein, so we have to go back to phenolphthalein because they drew an incomplete reaction. First one is excess hot NaOH. So this is phenolphthalein. So NaOH, will NaOH react well with phenols?
Well, because acid and base, so.
Okay, phenols are slightly basic. And if you go, remember you have to learn which ones are acidic, and the comparison of acids and bases must be somewhere here. Just a second. This is all about electrophilic substitution, C5 directing, acetylation, oxidation of arenes. Forget that. So that's oxidation of arenes. Where's the relative strength comparison of acids? So remember, you have to learn the comparison of acids. That you will have you have three types of molecules. You've got carboxylic acids, phenols, and alcohols. Alcohols are the weakest acids, and phenols are kind of in the middle, and carboxylic acids are like complete acids. And there's a table that you should know. The table must be somewhere here. So remember that carboxylic acids, they react with metals, they react with bases, they also react with carbonates, which are weak bases. Phenols, on the other hand, they don't react with carbonates because phenols are acids, but they're not that good of an acid. So this is only going to react with the Na or NaOH, while alcohols, they only react with Na, they're terrible acids. And even with Na, the reaction is really, really slow. And you should know the reasons for that. They might ask you for the reasons as well. But anyways, in this case, what will happen? The H will be lost and Na.
Yes.
Right? What will happen to the ester? What happens when you react NaOH? And we need to know, is this, it's excess hot NaOH. So what happens to an ester when you add NaOH? They get hydrolyzed. Remember, acids, esters, they break down in alkaline hydrolysis or acidic hydrolysis. So the ester is going to break in the middle. This part will form the alcohol back again. This part will form the carboxylic acid. Is this clear?
Yes.
And also remember that the carboxylic acid that is formed, because you're doing an alkaline hydrolysis, so that will also turn into a salt eventually, so it's going to be serial bond O minus 1 and Na plus 1. So that is going to be your brought it. And this one is your normal alcohol. Normal alcohols don't react with NaOH. So this one would remain OH. The one over here, that is going to remain OH. But this one, the carboxylic acid, will eventually end up reacting with the NaOH. Is this clear? Now he says in excess of Br2 is added. So in excess of Br2 without the catalyst. So you've got 3 benzenes. Which one will react with bromine without the catalyst? Like no catalyst is added.
Both the phenols will react with.
Okay, so phenols will react, and the phenols, the 2, 4, 6 positions, they would be, because it's a highly activated. And what's the reason? Phenols have an electron donating effect. The O overlaps, which increases the electron density on the phenol on this side. So bromine electrophile is going to be strongly attracted to this side. That one is a deactivating group. The electron density is getting pulled away, which is why the electron density is lesser. So it's not going to react with bromine. The 4th position is already occupied, so you can't add a bromine there. What's the next one? In excess of Br2, we did that. So this is a synthesis reaction that you were talking about. You're seeing that methyl orange can be synthesized as shown. So there's this thing going on. What compound is this one?
Diazonium azo compound.
It's an azo compound. It's an azodie. So how azodies? Let's go through azodies quickly. Not sure where they are. Just a second. This one. So azodies were that you started off with phenylamine that turned into diazonium ion, which is N triple bond N+1. That's a pretty strong electrophile. NaNO2 and HCl in temperature less than 10 because it's very unstable. If you heat it, it decomposes. If the temperature becomes greater than 10, it decomposes and turns into a phenol. It hydrolyzes in water. Anyways, the diazonium ion gets attracted to an activated benzene. Like it's either going to be a phenol or a phenylamine. Anything that's got lone pairs, that increases the electron density. So the positive charge will be attracted to it. Eventually, it's going to form the azo group. Now this one. So you have to do the reverse. So that means the molecules are given above. So that means it's breaking up over here. I mean, this thing is this, right? This is the activated benzene because the N lone pair is going to mix up with benzene's electron cloud and it's going to increase the electron density at 2, 4, 6 positions. The other side will be your, so that's going to be your N triple bond N+1, or we can just write N2 plus with SO3 -1, Na plus. And it's going to be interested in these electrons. Is this clear? So that's S. Is this clear?
No, sir, I don't get how you got that compound.
You see what happens. How does the azo group form? You got a benzene with N triple bond N+1 diazonium ion, which is your electrophile, which reacts with your with a benzene that is activated. That has it's supposed to be an activated benzene, which means it's either going to be a phenol or a phenylamine, because the lone pairs mixing with it will increase the charge density on positions 2, 4, and 6, right? Is this point clear?
Yes.
So when you have a diazonium ion, the electrons over here will get pulled, and this benzene and this benzene will connect with the N double bond in the middle. So he's doing the reverse now. So if you want to do the reverse, so one part breaks into this, the other part breaks into this, right? Is that clear?
Yes.
So you had an azodie, and I figured out it's going to break over here because they gave us one of the compounds. So I mean, this thing is this, right? Yes. so that means the N double bond N or the N triple bond N plus 1 belongs to this one, right? So it's going to come from here. Is that clear?
Yes, sir.
And one of them is going to be your activated benzene. So the other one is going to be your diazonium ion, which is going to act as your electrophile. So that's going to be your diazonium ion. And now before that, what happens before it's a diazonium ion? So let's go back. What happens before it's a diazonium ion? Before it's a
nitrobenzene?
No, that's even before that. I mean, that step isn't even included. Like, I mean, that is part, because I'll talk about that. Before that, it's an amine. And before that, it's a nitrobenzene. Is that clear? Like I can kind of add it over here, that we can include that step, but that is like, I mean, that's not needed. Or you can't say it's part of the same whole mechanism. So here's my benzene, and reduction of nitrobenzene, that will turn it into a phenylamine. So, and what is used for reduction?
For reduction, 10 and concentrated HCl.
It's going to be 10 plus concentrated HCl, and it turns the nitrobenzene into a phenylamine. So it turns it into a phenylamine, and we can. So that's NH2. Now, now the thing is that I mean, this step isn't really necessary because you already have phenylamine. So we start from that point onwards, and so the point was diazonium ion. Before that, it's going to be a phenylamine. Is that clear?
Yes.
So before this happened, this N2 plus 1 over here would have been NH2, right? And this side would be SO3 minus 1 Na plus. And before that, it's a nitrobenzene. So over here, it's 10 plus concentrated HCl. Over here, it's a NaNO2 plus HCl. And the temperature should be less than 10. And then below that, this one, you just add NaOH. That's your condition. You have alkaline condition, you just mix them up. So you add, and he didn't ask for that, I think. So suggest reagents for step 1 and 2, we did that. Okay, is this clear? This one?
Yes, sir.
So here's another one. Not related to, forget that. Now he's saying that there's this molecule, and he's saying it turns into C13H12, and then it turns into this thing. So he's saying benzophenone can be synthesized in 2 steps. So he's oxidizing it. So before oxidation, what is a ketone before oxidation?
Ketone, a carboxylic acid.
A ketone.
No. Alcohol.
It's an alcohol, and where's the? Just a second. There was oxidation somewhere. This is nitrogen compounds, and before, I think before that we did. This one. So remember, this is AS, oxidation of alcohols. Primary alcohols will turn into, primary alcohols will turn into ketones, and ketones will turn into carboxylic acids. So it would be a primary alcohol. An aldehyde and then a carboxylic acid. Ketones will turn into, if you reduce them, they would turn into secondary alcohols, and no oxidation for tertiary alcohols. Now, based on this fact over here, the thing is, he's saying deduce the identity of compound L and draw its structure. So if you just go back and now a ketone, now here's the thing that I don't think it's going to be that simple. One second. So the ketone part will turn into back to an alcohol. But the thing is, it doesn't make sense. I mean, this step number 3 doesn't make sense. It doesn't make sense. So he's saying, he's talking about step 3 now. So the thing is, we need to think, how are two benzenes getting connected to each other? What happened? He's saying can be synthesized in 2 steps. And over here, in 2 steps. And so that's a big question mark. So C13, H12. So C13, H12, there is no O, right? So that means that's wrong. I mean, there's no OH, right? So how do you have 13H? I mean, let's figure out C13 and H12 first. So that's 1, 2, 3, 4, and 5 carbons, hydrogens. That's 1, 2, 3, 4, and 5 hydrogens. So that's 10. 10, and this is 11th, and this is 12th. So there's no need for an OH. So that's probably the only likely, like C13H12, that's probably the only likely product that is kind of possible, right? And so that kind of means, what does it mean? It doesn't mean anything, actually. He's saying reduce the identity of compound L and draw its structure. So it's, I mean, this is probably going to be the most likely structure. I mean, you can't, I mean, that's the only possible structure. And he's saying name this. So the question is, how did it end up like this? That's the bigger question. So this carbon is positive. And if there's another benzene, and the bromine is negative, right? So it's basically a halogenoalkane. You're saying name the mechanism of step 3. It's probably going to be elimination. I think probably like what happens in elimination is that the bromine is lost and the H is lost from the neighboring carbon atom, but there is no neighboring carbon atom. You're saying name this and name the reagents and conditions for step 3. So the question is, how did they end up if I introduce the, I mean, we know step 4, deduce the type of reaction, that's oxidation, obviously. But this one, bromo, which paper is this? This is the latest one. So how did a halogenoalkane join up with another halogenoalkane? If it had bonded with the benzene, it would have made sense. Like the positive charge over here will be attracted to this one. So what mechanisms do halogenoalkanes have? Because he did talk about mechanism of step 3. Do you know what mechanisms do halogenoalkanes have?
Nucleophilic substitution?
So they have nucleophilic substitution, right? So they have a SN, I mean, this one will have SN2 mechanism because it's a primary halogenoalkane. But the thing is, let's substitute Br with, I mean, we can substitute Br with 3 things, OH, NH2N. I mean, because the benzene has nothing to do with this. It's just a normal halogenoalkane, a carbon chain with the bromine. So there are 3 substitution reactions. You can do it with NH3, you can do it with OH, and you can also do it with one more, which is CN. So the carbon chain length is not increasing, so that doesn't involve a CN. What about an OH? The Br got substituted by an OH. So you had two alcohols, but why would the two alcohols join up in the middle? That's a big question mark. So let me just check the mark. It's summer 20 MS42, just a second. MS42. Maybe in this question, they're just asking us to make a wild guess. Let's see what. Because nothing, C13 and H12 is fine, right? I mean, there's nothing wrong with C13 and H12. That is absolutely fine. So this one, we did this question. So we got that, right? And then he says, why is he saying electrophilic? Why is he saying electrophilic substitution? Doesn't make any sense. Benzene and AlCl3. Why is is this the right one? He's 5D1. Just 1 second. It is 5. Deduce the identity of compound L. We did identify compound L correctly. That is identified correctly. But how did electrophilic substitution end up here? Because nothing is getting substituted on the carbon itself.
I think
is there something?
benzene is getting substituted.
But
Br is leaving and it's getting substituted with the benzene ring, maybe?
But there should have been, I mean, it would have made sense. Yes, I think, is the reagent benzene? Are they saying the reagent is benzene? Then it makes sense. Yes, it is benzene. Now it makes sense. I was thinking that there were two of the same reacting. I didn't realize that there would be. So that makes sense now. So the reagent they were looking for was a benzene. So this positive carbon over here is going to get attracted to benzene, and the Br would, because of the electron density, would get knocked out. So this carbon atom over here is going to get attracted to, which is positive, would be attracted to benzene. So that makes sense. I was thinking that there were just two of the same molecules bonding to each other. That wasn't making sense. So is this clear?
Yes.
Right. So it's just an electrophilic substitution onto the benzene ring, where the positive thing, electrophile, gets attached to it. So that is electrophilic substitution. So benzene was the basic was the reagent. And is it making sense now, right?
Yes, it is.
So we made the mistake. We were thinking that there were two of the same compounds kind of joining up with each other. It wasn't two of the same compounds. It was another benzene that was basically connecting with that. And deduce so that's oxidation. Deduce the number of peaks that would be present in carbon-13 NMR spectrum of benzophenone, which is this one. So do you know about carbon-13 NMR? How many peaks would this have? How many different types of carbon does it have?
One. Yeah.
How many different carbon environments does it have?
Yes.
Like if I talk about, so if I talk about this carbon, right?
Yeah, this is a different environment.
What about, are these two carbon atoms exactly the same?
Yes, they are.
So that's
two different environments.
Let's wait. Are this carbon and this carbon and this carbon and this carbon, are they exactly the same environment, right?
Yes, they are.
And then you have This carbon and this carbon and this carbon, I mean, the surrounding bonds, etc., they're exactly the same, right? And the last one, the one that's at the end, that is different. I mean, these two are exactly the same. And the middle one was, I mean, this one was obviously different from all the others. So focus again. Focus on the bonding. Like, I mean, this carbon is bonding to a double bond. So its bonding is completely different to any of the carbon atoms in the molecules. This is unique. That's, let's call that the first one, right? Then the yellow ones. These two are bonding in exactly the same way. Is that clear?
Yes.
Then the pink ones, they're bonding in exactly the same way. Like this carbon has a carbon, the yellow carbon on one side. This carbon has a yellow carbon and a green carbon. This one also has a yellow carbon, and so the bonding and arrangement around them is exactly the same. So the pink ones are bonding in exactly the same way. Then the blue ones are bonding in exactly the same way. This one has this carbon over here and a pink one on its side. This one also has the same. It's got a carbon, so it's bonding in exactly the same way. So remember, when you're trying to identify peaks, that's going to be 1, 2, and 3, and that's 4 and 5. So there would be 5 different peaks. So remember, when you talk about benzene and you talk about carbon's environment, like if I have this molecule, how many different peaks would it have for carbon 13 NMR?
1.
So that is 1.
4 different peaks.
Huh?
4 different peaks.
Okay.
4 different peaks.
Okay. These two are exactly the same, right?
Yes.
And these two are exactly the same. While the one that's at the end, that is different. So there are 4 different peaks, right? The other part is reduce the forget that, identify 2 environments of carbon atom that would result in different chemical shift ranges in this carbon 13 NMR spectrum of. So you just have to open the data booklet and just go, like, you got a C double bond O. So you can talk about that, and you got a carbon benzene attached to. You can have a benzene carbon. You can go and have a look at that as well, and just quote the chemical shift. I mean, we can do that. Just a second. Like where is, this is infrared, and this is your carbon 13. So you got benzene type of carbon, that's 110 to 160, right? And which other one? You had a C double bond O, which was which one? I think this one. You had actually you had this one. I mean, this is the closest one. CO. He's talking about this C. I'm talking about the sp2 hybridized CO, which is going to be, it's this one. Is this clear? 192 to 220, right?
Yes.
And we didn't have this one, I think, because the neighboring had a CO, not a CH2. So we didn't have that carbon atom. Anyway, so where's our paper? This one. Now you've got reduce the type of polymerization shown here. What type of polymerization is this?
Condensation polymerization.
So that's condensation. Like if I draw this, it's something with an OH group on both sides. And the other one is C double bond O with Cl on both sides, right? So the H and the Cl are going to get removed. Over here, it's going to be OH, R, and OH again. So every time what will happen is that the H will be lost. And when the H is lost, the Cl is also lost. Cl and H are lost. And they're going to link up. So it is, so they're going to link up, and that the O remains. So they're going to link up. So that is what is going to get repeated over and over again. Now he's saying a polycarbonate formed from the diol P and COCl2. From the diol, what is diol P? I think it's this one. This is diol P. Draw one repeat units of Nalgene, one repeat unit. All you have to do is that this is your R group. I mean, this is the R group that was shown over here. It's a diol P, and you just have to enter this, and that's going to be a repeat unit. Is that clear?
Wait, how do you know what the repeating unit is?
They already told us that a diol reacts with this to form this COCl2 to form this polycarbonate, right? But the polycarbonate has an R in it. Like, you don't know what the R is, right? Now they're saying that Nalgene is a polycarbonate like this thing, formed from the diol P. Diol P, they gave you the diagram of diol P. Like this is diol P. It's an R group with OH on both sides, right? So this is your R with OH on both sides. Is the idea clear?
Yes, it is.
So basically the R that they're talking about, the diol over here, it's Nalgene, which is formed from diol P, this one. So this is your R. So you just have to get rid of the R, put this thing in the middle, replace the R. And Nalgene is a strong and tough polymer. Identify two types of intermolecular forces responsible for these properties. So first, look at this molecule. What type of intermolecular force will it have? Like if there's a acetyl bond O,
the
acetyl bond O is a permanent dipole. I mean, van der Waals is always there in any molecule. Acetyl bond O is going to be, it's going to result in polarity. This carbon will be positive, this oxygen will be slight negative. So that would result in permanent dipole interaction. Is that clear?
Yes.
And imagine the R over here in the middle. What type of intermolecular force will this R have? Is this a polar molecule? Or is this thing polar or non-polar? Like, it's just a bunch of carbon and hydrogen atoms all attached to each other.
It's non-polarizing because of the benzene ring.
So it's going to have van der Waals. And not only because of the benzene ring, because the carbon and hydrogen bonds are non-polar. So the OH would be gone anyways, because once condensation happens, I mean, the OH would be from the sides will be gone. So there wouldn't be any hydrogen bonding. So there's going to be van der Waals forces, and there's going to be permanent dipoles. And the group responsible for that. So you can talk about benzene. We can just have a quick look on this. I mean, this is the R that they drew. So IDID, that's instantaneous dipole induced dipoles or van der Waals forces, this thing. And the other one is permanent dipole. They didn't tell you which group was involved in A3. I mean, is this A3? So they didn't ask for the groups. Now he's saying proteins are polymers of amino acids. Complete the table to show how the secondary and tertiary structures of protein are stabilized. What happens in the secondary structure? Which intermolecular forces are responsible for the secondary structure and for the tertiary structure as well? Any idea? Let me open the board as well.
Hydrogen bonding, I think.
I'll just show this on the board. So the secondary structure is formed because of hydrogen bonds. 1 second. Just must be right at the bottom somewhere after. This is acids. Organic nitrogen compounds and so this one, this is where proteins, that's so this one, right? That you had a primary structure. The primary structure is a bunch of amino acids all lined up. And those amino acids, those amino groups, they bond with each other. So this is what an amino acid molecule looks like. A carboxylic acid on one side and an NH2 on the other side. So that's what your primary structure looks like. That what happens is that all these amino acids, they end up forming amide or peptide bonds between them. Like this is what a typical amino acid looks like. It's got a C, it's got an H. There's a carboxylic acid on one side. And there's an R group, right? And there are lots of these 20 different types of amino acids that make up any type of protein usually. And there would be a bunch of these. The R group would be different in each case. The OH would be lost and the H would be lost. The H would be lost from the amine. The OH would be lost. The H would be lost. They would form water, right? And these will link up with each other and they would end up forming amide or peptide links. Is that clear?
So can you repeat it once again?
See, this is the structure of an amino acid, like any amino acid. I mean, this is the structure of an amino acid. It's got, let me just do this. So you get a condensation reaction. All amino acids have these things. They have a carboxylic acid group, and they've got an amine group, and there's this carbon chain, an R group, which could be different for each amino acid. Is that clear?
Yes.
So what happens is that the OH and H, they form water. The OH and the H from the neighboring one, they end up forming water. And there's a condensation reaction. So these things, they disappear from the middle, even the side ones. So the OH and H are lost, and the molecules then get close to the residual molecules. They kind of get close to each other, and they end up forming bonds with each other. And every time there's going to be a sequence of R1, R2, etc., right? The R groups are going to be different. The R groups could be anything. So if you have an amino acid like over here, the amino acid come in many different shapes and sizes. So one example is alanine, where the R group is CH3. You got lysine, where the R group is a long carbon chain with NH2 at the end. So that is usually what amino acids, they kind of look like. Is that clear?
Yes.
Now, the primary structure is that they link up. And these amino acids, they're represented by their first three letters. Alanine, that's CH3. Glycine, the R group is H. Aspartic acid, the R group is CH2, and then there's a carboxylic acid, COOH. So every time the R group is different, otherwise the structure kind of looks exactly the same. So the primary structure is the order in which the amino acid are going to join up or link up when they bond with each other. Is that part clear?
Yes.
And then you have a secondary structure. The secondary structure is that when you look at an amino acid chain, you'll notice that it's got a lot of peptide bonds, serial bond ON, NH. When you have NH, what type of bonding will happen? There's going to be hydrogen bonds in NH, right?
Yes.
So think of this as a thread-like structure. Like there's a piece of thread. The thread will start coiling up. Why? Because the amide links will attract each other. So think of a long thread with a lot of amide links, like lots of other stuff, but lots of amide links and lots of very polar amide links. So one polar amide link will attract the polar amide link from another part of the same chain, and the thread will start to sort of coil up. Is that clear?
Yes.
And there are two ways in which it coils up. One of them is a beta pleated sheet, which is a completely flat structure and it's very rigid, where the chain kind of, this is what a beta pleated sheet would look like. Like this one. This just shows that, or maybe this one. This one is better. You've got one chain, you've got another chain, and they're all attracting each other. If you zoom in a bit, then you'll see the hydrogen bonding. The NH, the polar NH, the positive H, getting attracted to the lone pairs of oxygen on the other chain. Is that clear?
Yes.
And the other one, that's known as a secondary structure. The other one, so there are two ways in which it coils up. One of them is a beta pleated sheet. The other one is an alpha helix. Now, in an alpha helix, it coils up instead of forming a flat sheet. In an alpha helix, not sure that's a good alpha helix. Maybe this one. So in an alpha helix, it's still the same attraction, but now it's coiled up. Like the thread is coiling up on its own. The oxygen getting attracted to the positive H of the bottom chain, the positive H here getting attracted to the oxygen over here. Is that clear?
Yes.
So that's your secondary structure. You got two types of secondary structures. The coiling up is more flexible. The reason it's more flexible is because the coiled up structure is like spring-like. Like between one layer and the other layer, there are not enough hydrogen bonds, right? Because it's a very small coil, right? Do you get my point? Like in the alpha helix, one strand and the other strand will form a lot of hydrogen bonds. So that is why it's going to be slightly more rigid. While the alpha helix, because the coil is like really, really, really tiny, so the two chains, and the surface area would be lesser because one chain and the other chain, they won't be interacting that much with the top layer or the bottom layer because of the smaller size, right? Is this clear?
Yes, sir.
Now, an actual protein has both structures. It's got coiled up structures. It's got beta pleated sheets. If it has more alpha helix, the protein is flexible like spider silk. Now, there are other proteins. If you have more beta pleated sheets, then it's going to be stiff and rigid. Just like the human hair, you can't stretch it because it's very stiff. Your skin is kind of really soft and flexible. So it's got a lot of alpha helixes. So you can stretch it. And then the last thing that happens is that initially the structure that we drew, the carbon chain is not only going to have NH and serial bond O, it's going to have a lot of these R groups, these groups that are coming out of it, right? The R groups. Now, these groups will lead to a tertiary structure. Like once that folds up, the thread would then again fold up and coil up because the R groups will interact with each other, and the R groups can have any type of interaction because they're all kinds of R groups. Like one R group is a carboxylic acid, the other R group is an alcohol. They might end up together and form an ester in the middle. Or maybe one R group is carboxylic acid and the other R group is amine, and they would end up forming a salt like CO -1 and H+1, like this one. So there would be all sorts of hydrogen bonding, van der Waals, any type of R group interaction is possible because R groups, they come in many different shapes. Is this clear?
Yes, sir.
So it can be van der Waals forces, permanent dipoles, hydrogen bonds, covalent bonds, or ionic bonds. Any type of force of attraction would be possible. Coming. So secondary structure is due to the hydrogen bonds that are formed between what groups? Between your amide links. And your tertiary structure is due to a lot of things like covalent to ionic. Every conceivable force can be part of this tertiary structures, right? So groups involved. So for that, I'll just open the, like if I write covalent bond, then I'm going to look at the R group in the data booklet. I mean, there was amino acid somewhere, just a second. You've got amino acid R groups. So these are all the R groups, different R groups. And so ionic bonding can happen between carboxylic acid, which is glutamic acid, let's say glutamic acid, and lysine. Like this R group can become NH2+1 and that one could become CO2-1. Or you could have hydrogen bonding that can happen when you have OH as an R group, right? Is that clear?
Yes, sir.
So in this case, we'll also have a look at this. They'll probably accept a lot of things for this. Where's the... secondary hydrogen bonding between CO and NH. I wrote NH, the amide link completely, so I think that would probably be acceptable, but they were kind of being more specific. Like it's like the one that we showed in the images, I think over here. CO bonded to an NH. I just wrote that it's the amide link, the hydrogen bonding that's happening between the amide link. They were kind of being more specific. And so in this case, they're just asking any one of them because there's so many between the R groups. Is this clear?
Yes.
So, and then we can try. Let me open some worksheet questions. And let's stick to organic. So I wanted to do some. There's some really tough. Just looking for the same questions, the one that includes. Let's do this one. And slightly difficult. This one, he's saying that although now remembered for his music, forget it, product which is compound J shows the following properties. First one, J has this molecular formula. It's C4, H8, and O2. And it's neutral. It reacts with sodium metal. So if it reacts with sodium metal, what compound could it be? Like if it reacts with sodium metal, who reacts with sodium metal?
Acid like phenol or.
Okay, so it could be carboxylic acid. Can it be a phenol? Like, how can you guess that it has a benzene or not it doesn't have a benzene?
No, it cannot be because it doesn't have C6. It has C4,
Okay.
so it cannot be a
So
phenol.
remember this, for benzene, you at least need 6 carbon atoms. Anyways, it could be a carboxylic acid or it could be an alcohol. Alcohols also, remember, react with sodium metal. It reacts with Felling. Who reacts with Felling?
Felling aldehydes.
So aldehydes, they react with Fellings. And it does not react with aqueous bromine. So that means which thing is not present?
Double bond.
So no double bonds there, right? So he's asking the same thing. And then he says, the result of bromine test shows a functional group is absent. So we did that. Now in the boxes below, draw 3 possible straight chain structures. Straight chain means C4H8O2, right? So C4, that fit the above result. So straight chain, right? So we have to add an aldehyde. So aldehyde is double bond ON, H, right?
Yes.
So if all of them are kind of straight chain, so, and remember he's specific about straight chain, so everyone would have an aldehyde. That is a given. So all 4 will have aldehydes. So what about a no acetyl bond C? Plus, it might have a carboxylic acid or an alcohol. Now, if it has an aldehyde, which one can you rule out? I mean, if it has an aldehyde, we know it has an aldehyde. Then it can't have a carboxylic acid because you just have 2 oxygens, right? So 1 oxygen got used up in aldehydes. Is this clear?
Yes.
So for carboxylic acid, you need 2 further oxygens. So that would mean 3 oxygens. You don't have 3 oxygens. So you can't have carboxylic acid. So it must be an alcohol. And he already told us that it's neutral, so it can't be a carboxylic acid anyways. So it's neutral. It's neutral. So all you have to do is you can just place the OH at random places. Like the first one could be at the end of the chain, then you can have it on the second carbon atom, and then you can have it on the third carbon atom, right? That's pretty much all that you can do about it. And so those are your 3 structures. Is that clear?
Yes.
Now he says that it reacts with alkaline aqueous iodine with a pale yellow precipitate. So what's alkaline aqueous iodine? What test happens?
That's for methyl ketones?
Yeah, not just methyl ketones, methyl with the acetyl bond O. It could be an aldehyde as well. Like over here, it's just a test for this one. So this side could be a carbon chain or it could be a hydrogen. So methyl with acetyl bond O, methyl plus carbonyl. So, or there's another one actually as well. What is the other one? It's also a test for methyl and OH on the neighboring carbon atom. Right? Is this clear? So these 2. So which means it's this one. This one is methyl CH3. So yellow precipitate would be formed by this one. So this one will give an iodoform. The other ones don't have methyl group. This one has a methyl, but nothing next to it, right? Is this clear?
Yes, sir.
And ethane compound J exists as stereoisomers. Name the type of stereoisomers. What type of stereoisomers will this form? Like the entire molecule. Will it form cis trans or will it form optical?
Cannot form cis trans, I think. No, it cannot.
It cannot. Mainly because there is no double bond. So can it form optical?
Yes, it can.
So it's going to form optical because there's this carbon atom. So there would be, and they ask, yeah, that's a chiral carbon atom, and they're asking you to draw a sketch. So you'll so this is CH2 and then CHO, and this one at the bottom is H, and on the right side there is CH3. So there's going to be a mirrored version of the same thing. So you draw the two structures. Let's do this one. He's saying that two compounds V and W are isomers with the molecular formula C4H8O. This one O. First thing, by just looking at the formula, can it be is it an alcohol or an aldehyde?
An aldehyde.
I mean, or a ketone as well, but it can't be an alcohol because if it's, well, actually it can be an alcohol as well. I mean, there's a lot of,
yeah, it can be,
because you can have a double bond. You can change the number of hydrogens by adding double bonds between the carbon atoms. So both compounds react with sodium metal and both decolorize bromine. So both decolorize bromine, that means what is present? And sodium metal means OH, right? Because aldehydes and ketones don't react. Is that clear?
Yes.
So that means your O got used up with the alcohol part. So that means there is no aldehyde or ketone, right? No carbonyl compound. And then V forms a yellow precipitate with alkaline aqueous iodine. So that means in the case of V, since it is an alcohol and it's forming a yellow precipitate with alkaline aqueous iodine, so there must be CH3, CH, and next door there's an OH, right? And then he says when reacted with cold KMnO4, both V and W produce the same neutral compound, which is C4H10O3. Cold KMnO4. And both V and W. So the difference between them is that one has an iodoform, so I can plug in all the other things. There's got to be a double bond. So let's say that is V. And W doesn't have it's got a double bond. And maybe the OH is at the end. So it's not having an iodoform test, right? And two H's. Or for W, we actually, and he's saying both, they exist as stereoisomers. So the first thing is, there could be other versions of W as well. Like you could have double bond over here. And the OH could be at the end, right? There could be many different. combinations. But he's saying that they both make stereoisomers. So it can't be this one. I mean, this double bond will make stereoisomers, and this carbon atom over here is chiral. So that's what V and W are going to be. Is that clear?
Yes.
So the last part was important because they could make stereoisomers. So you had to look for molecules, which is why we rejected that. We knew that we had methyl with COH next door. And so I shifted the double bond to the next carbon atom. So that was V. And they all, if you add cold KMNO4, what will happen to them?
Oxidized. Will get oxidized.
To what?
Oh, no.
What happens when alkenes undergo mild oxidation? Like they turn into?
Carboxylic acids?
No, they turn into diols.
Oh, yes.
The OH get attached to. Now remember, alkenes had this had a number of different oxidation products. That strong oxidation for alkenes would result in a lot of things, like the double bond would completely break, and the product that you're going to obtain each side would depend on the number of hydrogen atoms. Like if this has 2 hydrogen atoms, it will turn into a carbon dioxide. If it has 1 hydrogen and 1 carbon chain, then this carbon will turn into a carboxylic acid. If it's got 2 carbon chains, then this carbon atom will turn into a C double bond O. Is that clear?
Yes.
So one thing, one second, let me. So is organic. You had to, in this case, 3 marks, explain the shape of the benzene molecule. So you should explain everything about benzene, that sp2 hybridized, carbon, and 120 degrees the angle. It's the carbon is trigonal, planar. The sp2 hybrid orbitals, they overlap and form sigma bonds between carbon atoms. Like this is what happens, that you have carbon atoms. So it's all the bonds are fan shaped, which are sp2 hybridized, right? And the p orbital, they overlap to form the pi electron cloud. So you have to describe everything about that, and it will be a planar hexagonal molecule, right? So the question is, write an equation. How is the electrophile generated in the nitration of benzene? You should remember this equation.
From HNO3 and H2SO4.
Yeah, but you have to also remember the entire equation, because he's saying write an equation for that. And it's going to form 2HSO4 minus 1, and I think NO2 plus 1 plus H3O plus 1, and that's where the NO2 plus 1 electrophile is created. And then he says, write down the intermediate. So where is the NO2 getting attached to? It's getting attached over here. So that means the NO2 plus 1 is coming in. And the benzene electron cloud would become, it's going to become partial at what point? At this point. There's going to be an NO2 and there's going to be an H. And these electrons over here would then be given back. Is that clear? Write an equation to show how the H2SO4 catalyst is reformed. So it is reformed because the HSO4 minus 1, the H plus 1 that leaves joins with the HSO4 minus 1. So that is how it is reformed. The H plus 1 leaves and it joins the HSO4 minus 1. So that's acting as a catalyst. It reforms at the end. For step 2, suggest the reagents and conditions and name the type of reaction. So, or step 2, what is step 2? NO2 turning into NH2. Nitrobenzene turning into NH2. How do you do that?
Benzene to NH2. Is it reduction?
It's reduction, 10 plus concentrated.
It's here.
It's here. Now I wanted to see if I have charts on this. Just a second. Because it's important that you should quickly know which thing goes into which, like how is one thing formed from the other, especially when it comes to synthesizing molecules. This is for so this one is for AS, I guess. Or is it for polyamides? That's 1 second. Not this one, this one. This one. Let me just see. Let me just send you these just 1 second. Galaxies. Okay, so there's this one here. So I'm going to send you these charts so you know what happens, which thing goes to. And this one is specifically for benzene. Is that clear? Like if you have a phenol, what happens to it if you add acyl chloride? What happens to it when you add Br2 aqueous? Dilute nitric acid, concentrated nitric acid. How is diazoniamines produced? How is azodized? So that's specifically for, this one is specifically for benzene. I'll send you the AS ones as well. Just wait, hold on 5 minutes, TK. Let me just. Uh, 1 second, A2. I'm sending you all of them. Just find which one you think is uh, better. It's not loading for some reason. You can see, you can pick any one of them. And I'll see if I have some other stuff. Okay. So let's continue tomorrow then.
Yes, sir.
Okay, Rajni. Take care.
Thank you.